Forgot to turn on the microphone. My video is not working very well, so I don't know whether we'll see the videos or not. Anyways, I believe we stopped at this slide, special and general rules of multiplication. Anybody confirm that? Yes, no? Okay, I don't hear anything, or see anything, so we'll move ahead. All right. Okay, so the special rule of multiplication requires that the two events A and B are independent. And two events A and B are dependent if the occurrence of one has no effect on the probability of the occurrence of the other. So can someone give an example of that? Of two independent events? It can be anything that you want to think of. Nobody can think of? Two dices? Okay, that's one, yeah. Because rolling one die and then a second die has nothing to do with each other. And tossing a coin, yeah. So those are the two. We're drawing cards out of a deck of cards. Except, remember, what's the exception? Does anybody remember what the exception is? If you return, right, or that's referred to as replacement, right, Wellington? Okay, so here's the example. A survey by the American Automobile Association, AAA, revealed 60% of its members made airline reservations last year. Two of the members are selected at random. Since the number of AAA members is very large, you can assume that R1 and R2 are independent. So what is the probability both made airline reservations last year? Oh, sorry. Okay, over here on the left side, the solution. The probability the first member made an airline reservation last year is 0.60, written as P for probability, and within the brackets R1, which is reservation 1, is 0.60. The probability that the second member selected made a reservation is also 0.6. So P of R2 equals 0.60 because they're independent. Since the number of AAA members is very large, you can assume that R1 and R2 are independent. Okay? And here at the bottom, we have the formula. P of R1 and R2 is equal to PR1 times P of R2, which is 0.6 times 0.6 equals 0.36 or 36%. That's the probability, okay, that the two random reservations are independent. So, talking about the general rule of multiplication, and we've gone over a little bit of this, which is P of A and B, which equals PA times the probability of P given A. Okay? So, example, a golfer has 12 golf shirts in his closet. Suppose 9 of the shirts are white and the others are blue. So that means there's 3 blue. He gets dressed in the dark, so he just grabs a shirt and puts it on. He plays golf 2 days in a row and does not do laundry. Well, he'll be pretty smelly. What is the likelihood that, oh, sorry, he does change. So what is the likelihood both shirts selected are white? So the event that the first shirt selected is white is W1. The probability is probability P of W1 equals 9 over 12. And if we reduce that, what do we have? If we divide the fraction by 3, what do we have? 3/4, and what's that percentage? 75%, right? So it's a 75% chance that the first shirt selected will be white. The event that the second shirt selected is also white is referred to as a conditional probability. That the second shirt selected is white, and that the first shirt selected is also white. Now remember, this is without replacement. So what happens is we only have 11 shirts now because the first shirt was chosen and gone into the laundry, so there's only 11. So you reduce the number of white shirts by 1. So it's 8 out of 11, which is, somebody can come up with the percentage or the decimal, 72. Okay, so if we determine the probability of 2 white shirts being selected, use the formula. P of AB is equal to P of A times the P of B given A. Straight line means given. Substitute in numbers. We have 9 over 12 times 8 over 11 equals 0.55 or 55%. Are there any questions about that? Does everybody understand these two rules? Excuse me. Yep. Okay, well, at least John and Wellington understand the rules. Okay, so I'm going to try to show the video now. And if it doesn't work, it doesn't work. And it's rather slow. All right. I think this is going to work, I think. All right. Oops, sorry. Oh dear. That's interesting. Okay. No, that's not it. Sorry. Okay. For some reason, it's not working on a Chrome.
Let's think about the situation where we have a completely fair coin here. I'll assume it's a quarter or something.
Okay, so hold on a second. For some reason, anybody ever have this problem where you cannot see a video on Chrome? I'm not sure why. My God. Very slow. Wow, it is extremely slow. Yeah, I could if I had it. I was using Safari.
Let's think about the situation where we're completely fair coin
Oh,
here.
interesting.
I'll assume it's a quarter or something. A quarter. Just a tenth a quarter. A profile or just a tenth. That'll do. It's a fair coin,
okay.
And we're going to flip
Hold
it.
on. Oh my
fair
God.
Coin. We're going to flip Let's start with a straightforward one. Let's just flip it once.
Well, I can hear it.
One flip coin. What's the probability of getting heads? Let's think about the situation where we have a completely fair coin here. I'll assume it's a quarter or something. A quarter.
You can hear it, right?
A profile of George Washington. That'll do. So it's a fair coin. And we're going to flip it a bunch of times.
I'm not sure why it's not going.
So let's start with a straightforward one. Let's just flip it once. So with one flip of the coin, what's the probability of getting heads? Well, there's two equally likely possibilities, and the one with heads is one of those two equally likely possibilities, so there's a 1/2 chance. Same thing if we were to ask, what is the probability of getting tails? There are two equally likely possibilities, and one of those gives us tails, so 1/2. And this is one thing to realize. If you take the probabilities of heads plus the probability of tails, you get 1/2 plus.
You can't see the video, eh? Not sure why. I'm going to try one more thing. Oh, yes, you can't? Or yes, you can? You can see it. Oh, all right. Okay. We cannot see it, so not for me. All right. I'm going to try one more thing if it works. Oh, dear. Oh, not a good day. Okay.
Let's think about the situation where we have a completely fair coin here. I'll assume it's a quarter or something.
Okay, I'm just going to. You can hear it, but you can't see it.
Profile of George Washington. That'll do. So it's a fair coin. We're going to flip it a bunch of times and figure out this. So let's start with a straightforward one. Let's just flip it once. With one flip of the coin, what's the probability of getting heads? Well, there's two equally likely possibilities, and the one with heads is one of those two equally likely possibilities, so there's a 1/2 chance. Same thing if we were to ask, what is the probability of getting tails? There are two equally likely possibilities, and one of those gives us tails, so 1/2. So let's think about the situation where we have a completely fair coin here. I'll assume it's a quarter or something. A quarter. I just attempt profile of George Washington. Well, that'll do. It's a fair coin, and we're going to flip it a bunch of times and figure.
Okay, I just want to check. Can people hear and see this or not? No, we can hear but not see. All right. Okay, so let me play it, and if you've got questions, I'll try it again later. I'm not sure why it's not working. I'll try it again. I apologize, everybody. Oh dear.
Figure out the different probabilities. So let's start with a straightforward one. Let's just flip it. So with one flip of the coin, what's the probability of getting heads? Well, there's two equally likely possibilities, and the one with heads is one of those two equally.
Okay.
So there's a 1/2 chance. Same thing if we were to ask, what is the probability of getting tails? There are two equally likely possibilities, and one of those gives us tails, so 1/2. And this is one thing to realize. If you take the probabilities of heads plus the probabilities of tails, you get 1/2 plus 1/2, which is 1. And this is generally 2. The sum of the probabilities of all of the possible events should be equal to 1. And that makes sense because you're adding up all of these fractions, and the numerator will then add up to all of the possible events. The denominator is always all of the possible events, so you have all of the possible events over all of the possible events when you add all of these up. Now let's take it up a notch. Let's figure out the probability of, I'm going to take this coin and I'm going to flip it twice. probability of getting a heads and then getting another head. Probability of getting a head and then another head. So there's two ways to think about it. One way is to just think about all the different possibilities. I could get a head on the first flip, a head on the second flip, head on the first flip, tail on the second flip. I could get tails on the first flip, heads on the second flip, or I could get tails on both. So there's four distinct, equally likely possibilities, four distinct, equally likely outcomes here. And one way to think about it is on the first flip.
Okay, I'm just going to ask a question. Are those four independent events or dependent? Everybody? Why is it dependent, John? Amir, why is it independent? Can someone explain why it's dependent or why it's independent? Why are the four events dependent or independent? Nobody can explain. We just went over that independence and dependence. Okay, an independent event mean is not dependent on the last, whatever it was doing, right? So when you flip a coin, if you flip it the first time, is the second time dependent on the first time? No, exactly. That is the definition of independent events. Okay? So his condition here is he's flipping the coin twice. Right? He wants to see what he can end up with. There's four possibilities. Heads, two heads, head and a tail and a head, and two tails. The second flip of the coin is not dependent on the first flip. So, therefore, they are two independent events. Okay, does anybody have a question about that? Okay, we'll continue.
I have two possibilities. On the second flip, I have another two possibilities. I could have heads or tails, heads or tails. So I have four possibilities. For each of these possibilities, for each of these two, I have two possibilities here. So either way, I have four equally likely possibilities. How many of those meet our constraints? Well, we have it right over here. This one right over here, having two heads meet our constraints. So there's only one of those possibilities. I only circled one of the four scenarios. So there's a 1% chance of that happening. Another way you could think about this, and this is because these are independent events, and this is a very important idea to understand in probability. We'll also study scenarios that are not independent. These are independent events. What happens in the first flip in no way affects what happens in the second flip. And this is actually one thing that many people don't realize. Something called the gambler's fallacy, where someone thinks if I got a bunch of heads in a row, then all of a sudden it becomes more likely on the next flip to get a tail. That is not the case. Every is an independent event. What happened in the past in these flips does not affect the probabilities going forward. So the probability of getting a heads on the first flip in no way, for the fact that you got a heads on the first flip, in no way affects that you got a heads on the second flip. So if you can make that assumption, you can say that the probability of getting heads and heads, or heads and then heads, is going to be the same as getting probability as the probability of getting heads on the first flip times the probability of heads on the second flip. We know the probability of getting heads on the first flip is 1/2. The probability of getting heads on the second is 1/2. So we have 1/2 times 1/2, which is equal to 1/4. Which is what we got when we tried out all of the scenarios, all of the equally likely possibilities. Let's take it up another notch. Let's figure out the probability, and we've kind of been ignoring tails, so let's pay some attention to tails. The probability of getting tails, and then heads, and then tails. So this exact series of events. So I'm not saying in any order, two tails and a head. I'm saying this exact order. The first flip is a tails, second flip is a heads, third flip is a tail.
Okay, so Remember, this does not change whether they're independent or dependent. In this situation, they're always independent events. So always remember that one event is not affecting another event.
Once again, these are all independent events. The fact that I get tails on the first flip in no way affects the probability of heads on the second flip, and that in no way affects the probability of getting tails on the third flip. So because these are independent events, we can say this is the same thing as the probability of getting tails on the first flip times the probability of getting heads on the second flip times the probability of getting tails on the third flip. And we know these are all independent events. So this right over here is 1/2 times 1/2 times 1/2. 1/2 times 1/2 is 1/4. 1/4 times 1/2 equal to 1/8. So this is equal to 1/8. And we can verify it. Let's try out all of the different scenarios again. So you could get heads, 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 tails. You could get heads, tails, heads. You could get heads, tails, tails. You can get tails, heads, heads. This is tricky sometimes. You want to make sure you're being exhaustive in all of the possibilities here. You could get tails, tails, heads, tails. You could tails, tails, heads, or you could get tails, tails, tails. And what we see here is that we got exactly 8 equally likely possibilities. We have 8 equally likely possibilities. The tail, heads, tails is exactly one of them. It is this probability right over here. So it is one of 8 equally likely possibilities.
Okay. Okay, I'm glad you could see that. Well, let's go back to the PowerPoint. Very slow. And every time I go back, I have to go back to, goes back to the first slide. All right. There's a lot about probability, whether you want to know that or not know that, but there are lots of different aspects of probability. So we're going to talk about conditional probability, which can be thought of as looking at the probability of one event occurring with some relationship to one or more other events. So for example, event A is that it's raining outside and it has a 0.3 or 30% chance of raining today. Event B is that you will need to go outside, and that has a probability of 0.5 or 50%. A conditional probability would look at these two events in relationship with one another, such as the probability that it is both raining and you will need to go outside. So the formula for conditional probability down here, the probability of B, where you need to go outside, given A, is the probability of A and B, they're both going to happen, divided by the probability of A, which can also be written as the probability of B given A equals the probability of A. And who can remember what this sign means? Because you'll see it a few times. Is it the union or is it the intersection? There's a clue. Intersection, right? Because the upside down one, or the one that looks like a U, is union, which means and this is A and or B. Okay, the intersection divided by the probability of A. All right, I'm going to try and get the video. Sorry. it's very slow. Sorry, my computer seems to be slow, or the connection seems to be slow. Okay. Whoa, it's very slow.
Let's think about a situation where we have a completely fair.
Oh my God, I don't know what's going on here. That is weird. Sorry. And that's why I prefer to be in the classroom. Oh my God, the same thing happened. I'm not sure why. Anyways, when you look at conditional probability, there is some kind of dependence, because if something happens, you also have to do something else that is occurring while the other event is occurring. That is conditional probability. Okay? So when you say, if this happens, then this may happen. Or if this occurs, then this may occur. Does everybody understand that? Holy moly. And this video is not working up there. Okay, let's see. No, it doesn't seem to work. Not sure why the other video worked. Okay. So I'll just suggest that you look at the video, and it's explaining conditional probability. I'm just going to check one more thing here. If I have it, I'll see if I have Firefox. I don't think I do. And I do not. Okay. Sorry about that. All right, we'll continue. Okay. So continuing with conditional probability. So an example in real life, it's used in many areas, including finance, insurance, and politics. So for example, how appropriate, the re-election of a president is on the voting preference of voters and perhaps the success of television advertising, given the probability of the opponent making gaffes during debates. Okay? Has anybody noticed, or does anybody pay attention to the presidential election in the States? Do you notice anything? Is there something that has occurred that you've noticed that may change the way people are going to vote? No, nobody's noticed, or nobody cares? Yeah, COVID. Okay, so I mean, what does that mean? Does that mean more people will vote for Trump or more people will vote for Biden? Why do you say that? Yeah, but that doesn't tell me why. What does COVID have to do with the voting preference? Remember, this is a conditional. Okay. Taratha, you have to explain we're talking about probability here. If one condition exists, how does that change the second condition? Okay. The question is, will people believe that? Will the majority of the people believe that? Or the majority, or it doesn't have any effect on people? You're given a condition. There's COVID. Saying there's a probability that more people will vote for Trump than, or more people will vote for Biden than they will vote for Trump. Okay, why? This is the point of when you're doing statistics, you have to explain why. What is that relationship? Can someone tell me what that relationship might be? Nobody? Okay, you have to understand this. All right, maybe we'll look at the second example. The weatherman might state that your area has a probability of rain of 40%. Okay? However, this fact is conditional on many things. The probability a cold front is coming to your area. The probability of rain clouds are forming. The probability of another front pushing the rain clouds away. We say the conditional probability of rain occurring depends on all of the above. I will just give you a little anecdote. I think I mentioned that my son, who just actually started working for a company in Nova Scotia, as a forecaster, what he told me, he went to McGill, and I don't know if people are aware, there are satellites that go around the Earth. They're weather satellites, and they look at the conditions, and each satellite has a model, and each model has a number of factors that produce a forecast. So I'll just give you an example. There's one called the British model because there's a British satellite that goes around the planet. And believe it or not, they don't all have the same factors. So each model measure the weather conditions to see how accurate the forecasts are. And believe it or not, the British model is the most accurate forecaster for Canadian weather. It sounds silly, but I mean, it's just a satellite going around, and it was by the British. Okay. Plus, each of the satellite models has about 50 factors in it. So just so you know that you know, not boggled out of your mind, this example has 4 factors. Okay? But in reality, when somebody makes a forecast, they use the satellite, and you know, of course, there's going to be some factors that are the same, and they're going to give you the same results. But there are certain others that make one forecast more accurate than another forecast. So hopefully I didn't confuse you more. Anyway, okay. That is conditional forecasting. All right. So we're going to talk about Bayes' rule. Has anybody ever heard of, or has anybody ever done Bayesian mathematics? Nobody's heard of it? Nobody's done it? Nope. Okay. This is probably the first and the last time you're ever going to use it. Okay? So, the synopsis of the conditions for Bayes' rule. The tests are not the event. You have a cancer test, you separate from the event of actually having cancer. You have a test for spam. It's just bad mail, separate from the event of actually having a spam message. Tests are flawed. Tests detect things that don't exist, which is referred to as a false positive. Does everybody know what a false positive is? Does somebody not know what that is? Does anybody, have you heard of what a false positive is? Never heard of it. Okay, so let me explain. So for example, with COVID, they test people. Somebody may get a false positive, which means that it's really not positive. It means negative. So when we talked about a little bit about margin of error, you say, well, with 95%, we looked at confidence interval. Say with 95% confidence, okay, you're going to get this result. There's always a 5%. The other 5% that adds up to the 100% is what's referred to as the error. Okay, so some people, if they get a COVID test, may end up with a false positive, which means they really don't have COVID. It's just by chance that this will happen. And that is what a false positive is. There's also something called a false negative, which means maybe somebody tested negative for the test, but really they do have COVID. And that's much more serious than a false positive, obviously, in this case. So any questions about that? That's more covered in the next course, if people are going to take that STAT1010, because people have to be careful, and that's why you always have a large population, because the chances of that happening, and depending on your confidence interval, 95 or 99%, you only have 1 to 5% of your data giving these false positives or false negatives. So you, as a researcher, doesn't say, oh my God, this is what's happening. So I accept my hypothesis, my null hypothesis. Anyways, I want to get into that. I just wanted to give you information about that. So tests give us test probabilities, not real probabilities. People often consider the test results directly without considering the error test, like we just talked about. False positives skew the results. Suppose you're searching for something really rare, 1 in a million. Even with a good test, it's likely that a positive result is really a false positive than somebody in the 999,999. Okay? People prefer natural numbers, saying 1 in 10,000 rather than 1% helps people work through the numbers with fewer errors, especially with multiple percentages. And of those 100, 80 will test positive rather than 80% of the 1% test positive. So even science is a test. And at the philosophical level, science experiments can be considered potentially flawed tests and need to be treated accordingly. So there's a test for a chemical or a phenomena, and there's even an event of the phenomena itself. So our test and measuring equipment have some inherent rate of error. That is very important. So no matter what somebody's going to tell you, there are no tests that are 100% accurate. Okay? That is also referred to as the margin of error. Great. I'm going to try and get the next video, and hopefully it might work, it might not work. Okay. Interesting. It doesn't appear to be working. Let's see if this works. Nope, didn't work. All right, well, we'll continue here. I apologize, but remember you've got the PowerPoint so you can look at them. So continuing with Bayes theorem converts the result from your test into the real probability of the event. So for example, you can correct for measurement errors. If you know the real probabilities and the chance of a false positive and a false negative, you can correct the measurement errors. You can relate the actual probability to the measured test probability. Bayes' theorem lets you relate the probability of A given X, the chance that an event A happened given the indicator X, and the probability of X given A. So the chance the indicator X happened given the event A occurred. So given mammogram test results and known error rates, you can predict the actual chance of having cancer. If we look at an example here, the anatomy of a test. An article describes a cancer testing scenario. 1% of women have breast cancer and therefore 99% do not. So remember, you always remember that whatever you're doing is either going to add up to 1 or it's going to add up to 100%. And if you look at that, 1% of women have breast cancer. The complement is 99% do not. 80% of mammograms detect breast cancer when it is there, and therefore 20% miss it. 9.6% of mammograms detect breast cancer when it's not there, and therefore 90.4% correctly return a negative result. Okay, does everybody understand how those numbers work? Does anybody not understand? Look at the chart here below. You can see the probabilities. Somebody has cancer. The test is positive 80% of the time. Somebody has cancer and the test is negative 20%. This is the false negative. Okay? The test said they were negative, but they really may have had cancer. And the people who have no cancer, we tested positive 9.6%, and the test for negative was 90.4%. Okay, is there any questions about reading the chart? No questions? All right. Okay, so how do you read it? 1% of people have cancer. Just go back. Whoops. Okay. So if you already have cancer, you are in the first column. Okay, this column. There's an 80% chance you will test positive, and there's a 20% chance you will test negative. Okay? 1% times the 80%, 0.008, and that's a true positive. 1% times the 20% equals 0.002 is what's referred to as a false negative. Okay? If you don't have cancer, you're in the second column, no cancer. There's a 9.6% chance you will test positive and a 90.4% chance you will test negative. Okay? So 99%, this is where the 99 comes from, and here the 1% comes from here. So 99 times 9.6% is 0.09504. And if you're looking at true negative, 99% times 90.4% equals 0.89496. So there you have the real probabilities. You're multiplying, it's like, because you know from the population, not from the sample, from the population, that 1% of, in this case, I think it's women, cancer, 99% do not have cancer. So the results you get produce these results. Okay? So suppose that you get a positive test result. So what are the chances you have cancer? 80%, 99%, 1%. Okay? So what are the chances? You got a positive result. It means you're somewhere in the top row, either here or here. Okay? Don't assume anything. It could be true, it could be a true positive or a false positive. So the chances of a true positive equals the chance you have cancer times the chance test caught it. 1% times the 80% equals 0.008. The chances of a false positive, the chance you don't have cancer times the chance the test caught it anyway, is 99%. Times 9.6% equals 0.09504. So if you look in the first row, test positive, you see the true positive and the false positive. And that's what the table looks like. So, what's the question again? What's the chance you really have cancer if you get a positive result? So the chance of an event is the number of ways it could happen given all possible outcomes. So the probability equals, is the desired event divided by all possibilities. So the chance of getting a real positive result is 0.008. The chance of getting any type of positive result is the chance of a true positive plus the chance of a false positive, 0.008 plus, not multiplied, plus 0.09504 equals 0.10304. So the chance of cancer is 0.008. Okay, that's getting a positive result divided by the chance of a false positive, 0.10304, equals 0.0776, or about 7%. Right? And interestingly enough, the positive mammogram only means you have a 7.8% chance of cancer, rather than 80%, the supposed accuracy of the test. So it might seem strange at first, but it makes sense. The test gives a false positive 9.6% of the time. That's relatively high. So there will be many false positives in a given population. So for a rare disease, most of the positive test results will be, I tend to say, incorrect, not wrong. Okay? They say wrong. So if you want to test the intuition by drawing conclusion from simply eyeballing the table, if you take 100 people, only one person will have cancer, 1%. And they're most likely going to test positive with an 80% chance. Of the 99 remaining people, about 10% will test positive. So you'll roughly get 10 false positives. Considering all the positive tests, just 1 in 11 is correct. So there's a 1 in 11 chance of having cancer given a positive test. The real number is 7.8%, which is closer to 1 over 13 computed above, which you saw here. Okay, but you found a reasonable estimate without a calculator. Well, you did in your head or a calculator. Okay, are there questions about this, about how you get a real result? This is Bayes' theorem. This is how you apply it. All right? Are there any questions about this? Any comments about this? Yes, it's complicated. Well, if you follow the steps, it's not that complicated. Okay? But you have to have most of the data to figure out the theorem. And you formula sheets, so they're given to you, so you don't worry about that. Okay. I can't remember. There may be one, maybe two questions on the test about Bayes' theorem. Okay. But in general, does everybody understand the steps that you go through to come up with a solution? Yep. Okay. All right. So I know the formula looks intimidating. Don't worry about it. So you can't process above into an equation, which is Bayes' theorem. It lets you take the test results and correct the skew introduced by false positives. You get the real chance of having the event. So here's the equation. Okay, you want to find the probability of A given X. So on the top of the fraction, you have the probability of X given A times the probability of A. On the bottom of the equation, or sorry, the fraction, you have the probability of X given A times the probability of A. It's the probability of X not given A times the probability of not A not happening. So if we look at the sort of the key here, the probability A given X is the chance of having cancer given a positive test X. This is what we want to know. That's this probability of A given X. So how likely is it to have cancer with a positive result? We figured it out in the previous slides. It was 7.8%. The chance of a positive test, X, given that you had cancer, A. This is the chance of a true positive, 80% in this case. The probability of A is the chance of having cancer, 1%. The probability of not A, the chance of not having cancer, is 99%. Remember that table that we looked at. The probability of X given not A. So it's the chance of a positive test, X, given that you didn't have cancer. This is a sign for not A. This is a false positive. Okay? So false positive says, oh, you have it. In reality, you don't have it. And in this case, the number is 9.6%. So what it comes down to is the chance of a true positive result divided by the chance of any positive results. And you can simplify the equation to the following. The probability of A given X equals the probability of X given A times the probability of A divided by the probability of X. What's important for you to understand is the law that's involved in coming up with the theorem. You're going to have the formula. I don't expect you to memorize that. Okay? So I think people understand the logic. You can go over the example again. You have that to work with. So continuing, the probability of X is what's referred to as a normalizing constant. It helps scale the question. Without it, you might think that a positive test result gives you 80% chance of having cancer. The whole point of Bayes' theorem is basically it's a correction for the results. I'll give you an example. I don't know if anybody had this happen to them. Say you're in high school and the average on a test was, let's say, 92. Okay, that's rather high. So I don't know whether your teacher did this or teacher didn't do this. What you can do, and we talked about a little bit, is you standardize the results. Make it more like a bell curve. So you're correcting what happened. Whether the test was too easy, whether everybody knew what the answers, whatever it was. So basically, Bayes' rule is a correction. Okay? It's correcting the results. Does everybody get that? Any questions about that? No questions. Is everybody still awake? All right. So the probability of X tells tells you the chance of getting any positive result, whether it's real positive in the cancer population, 1%, or a false positive in the non-cancer population, 99%. So it's like a weighted average and helps you compare against the overall chance of a positive result. So you can think of it that way. So in this case, the probability of X gets really large because of the potential for false positives. Thank you. Normalizing constant for setting us straight. This is the part many people neglect, which makes the result 7.8% counterintuitive. Oh, you don't understand why you have to correct it. So if you consider a real population, you do some tests, which shines light through the real population and creates some test result. If the light is completely accurate, the test probabilities and real probabilities match up. Everyone who tests positive is actually positive. Everyone who tests negative is actually negative. This is not true, because when you may not be able to test a full population. Maybe millions of people. Maybe you're testing 100, 1,000. It's still not close, okay? It approximates the population. So therefore, you have errors. So in the real world, tests go wrong. Sometimes the people who have cancer don't show up in the tests, and the other way around. Bayes' theorem lets you look at the skewed test results and corrects for errors, recreating the original population and finding the real chance of a true positive result. So it's used as a corrective technique for possibly skewed results. Okay? Any questions about that? No questions. All right. So we'll just go through this. This is not something you're probably going to do, but you should know about. Okay, Bayesian spam filtering. If I'm pronouncing it incorrectly, pardon me. One clever application of Bayes' theorem is in spam filtering. You have an event A. The message is spam. Okay? I assume people still get spam messages. I mean, I do. Anybody not get a spam message? Anybody? You don't want to clean your ducks? Yeah, you get a lot, Wellington. Okay. You get spam calls, right? Yeah, almost every other day. Okay. All right. So this example is about spam filtering. So the event A is the message is spam. The test X is the message contains certain words, X. So the probability of spam given the words is equal to the probability of words given spam times the probability of spam divided by the probability of the number of words. Bayesian filtering allows you to predict the chance of a message is really spam given the test results, the presence of certain words. So clearly, words like Viagra have a higher chance of appearing in a spam message than in normal cases. I don't think many of you were going to get those messages, but anyway. Spam filtering is based on a blacklist is flawed. It's too restrictive and false positives are too great. But Bayesian filtering gives you the middle, so you use probabilities. As you analyze the words in a message, you can compute the chance it is spam rather than making a yes-no decision, which you want to do. If a message has 99.9% chance of being spam, it probably is. As the filter gets trained with more and more messages, it updates the probabilities that certain words lead to spam messages. And advanced Bayesian filters can examine multiple words in a row as another data point. So this is probably something I'm sure. I know that George Brown actually has a spam filter. I don't know what the algorithm is. I don't know what words they look at. I don't know if it's had a problem with somebody trying to send mail to your George Brown account, because usually they can't, even if it's from Gmail, because they have a spam filter. And I believe They can send it? Amir telling me yes, especially in your first year? Really? You got lots of spam messages? You're using your George Brown account. That's interesting. I know a couple of years ago when I was telling the students this, it was nice. There was no spam messages. Okay, so what do you mean, Amir? Not spam? What was it? It was? Or you're not sure? The personal emails. You know what? It depends because the computers at George Brown are going to look at the words. They're not going to look at the email. They're going to look at the words. So I'm surprised that you got personal emails. It doesn't catch everything, but this is an example of using Bayes' theorem, okay, to correct for mails because it could be extremely restrictive. And I mean, they could stop all spam all by saying, if, think about it yourself. If I get an email and if the address of the person sending the email is not a George Brown email account, don't accept it. Really? Okay. Oh, with your Gmail. Yeah, because it's not going to accept it. Yeah. So I think they've almost filtered out almost everybody's, like, another mail client, like Gmail or I can't remember now. My son uses it. But I just want everybody to understand that's how you can use the Bayes filtering to do something like that. So you know what the application of Bayes' theorem can be. Remember, it's altering, and it's giving you more of a true result than the results that may happen. Okay. So I'm going to try this one, and we'll see if this works. Probably won't, but whatever. Okay. Mm-mm-mm. Oh, sorry. I apologize. I had this all set up, and it didn't work. Let me see if this one works. Oh, nothing. All right. Sorry, everybody. Hopefully I'll get this fixed by Friday. And doesn't seem to be doing. My machine is very, very slow. Oh, I may have something here. Hello? No, it's not working. No. Okay. Sorry. This test is going to be hard. No, Amir. Is that a probability? Is that based on your understanding? Lots of material. Yep. It's a very long chapter. Anyways, this is the last topic of chapter 4. Contingency tables, or as they're usually referred to, the crosstabs. Okay, you're using subjective probability, Amir. You know how well that works. All right. Contingency tables, also called crosstabs or two-way tables, are used in statistics to summarize the relationships between several categorical variables. A contingency table is a special type of frequency distribution table where two variables are shown simultaneously. So, for example, a researcher might be investigating the relationship between AIDS and sexual preference. The two variables would be AIDS and sexual preference. The question is there a significant relationship between AIDS and sexual preference? And they pronounce chi, C-H-I. A chi-square test could then be run on the table to determine if there's a relationship between the two variables. So here's an example. A sample of executives were surveyed about their loyalty to their company. One of the questions was, if you were given an offer by another company equal to or slightly better than your present position, would you remain with the company or take the other position? The responses of the 200 executives in the survey were cross-classified with their length of service with the company. So what is the probability of randomly selecting an executive who is loyal to the company and would remain and who has more than 10 years of service? Okay, if we look at this. Okay, so this is the table. This is what's called a crosstabs table. So if we look, this is the title, length of service. Here's the columns, less than 1 year, 1 to 5 years. This is working for the company, 6 to 10 years, and more than 10 years. And the question was, so would they leave or would they stay? So you have would remain, A1, would not remain, A2. So you have the numbers. Remember, these are frequencies. Okay, you have 10-25, 30-15, 5-10, 75-30. And remember, in one of the videos, we talked about marginal totals. This is the marginal total. Remember, when we had margins of probabilities and you could figure out exactly what probabilities were inside each other, as long as you had margins or you had one result, you know everything adds up to 100%. So these are the totals for each of the columns. These are the totals for each of the rows. And this is the grand total. So you had 200 responses. Okay? So if you look at the table, the question is, what is the probability of randomly selecting an executive who is loyal to the company and would remain and who has more than 10 years service? So this is more than 10 years, correct? And you have 75 people saying they would remain. So what is the probability of that condition where an executive who has 10 years of service would stay with their company? Remember how you do it. The numbers are there. So what do you have to figure out? Can someone tell me? What's the probability of somebody with more than 10 years of service who wants to remain? What do you have to do? Exactly, Wellington. 75 divided by 200, which is? What's 75 divided by 200? 37.5%. Okay, so you answer the question. You're looking at these tables. I mean, that's a relatively easy one, right? You want to know if somebody who's a long service employee is going to remain if they had been given an offer that was a little better than what they currently have. So 37.5% of long service employees would remain. We'll just go over it. So event A1, which is this, they would remain, happens if a randomly selected executive will remain with the company despite an equally or slightly better offer from another company. Since there are 120 executives out of the 200 in the survey who would remain with the company, okay, look at these totals, 120 divided by 200, or 0.6 or 60%. Event B4, because we're looking at people with long-term service of 10 years or more, happens if a randomly selected executive has more than 10 years of service with the company. Thus, the probability of B4 given A1 is a conditional probability that an executive with more than 10 years of service would remain with the company. So of the 120 executives who would remain, 75 have more than 10 years of service. So the probability of B4 given A1 is 75 divided by 180. Okay, and the probability of A1 and B4, A1 is they would remain, and B4 is more than 10 years, is equal to the probability of A1 times the probability of B4 given A1, 120 divided by 200 times 75 divided by 120 is 9,000 over 24,000 or 0.375. But you can also just look at the table. Oh, here, they've got 10 years. This is the total. 75 divided by 200 would get you 0.375 or 37.5%. Does everybody understand the logic of doing this? Looking at the table and coming up with your probability. Any questions about that? No questions? Okay. All right. Has anybody heard of tree diagrams? Nobody's heard of tree diagrams? You did? Jonathan? Okay, what are they? Can you describe what they are? You know what they are? What do tree diagrams do? No, you've heard of it, but you don't know what they are. They show us a subset of what? Amir, it's stats. How many times do I have to tell you? You have to elaborate. You have to explain what it is. Like what the tree diagrams do. I mean, you said you knew what it was. Of a particular thing that we are looking for. You think that's a good answer? No, Amir, you're not. You have to be very explicit and give exactly the information. I'm just telling everybody this is more pertinent to your case study, your research. Okay, you can't just make statements and somebody has to assume what you're saying. No, you do know how to explain it. You just have to be calm and figure it out in your head. Okay, but Jonathan is correct. It shows the possible results for actions that require consecutive tests. That's part of it. But it shows you all the possible results. It shows you it's this condition, when it's that condition, if this happens, if this doesn't happen. So it allows you to figure out all the possible results, what it also does, it also gives you the space. So you know all the possible results are going to be. I'm going to try and get the video for this. And unfortunately, if it doesn't work, I apologize. And I don't know why this doesn't work. And that didn't do anything. And this doesn't do anything either. Okay, sorry about that. I will try to fix that. Okay, so tree diagrams allow you to see all the possible outcomes of an event. So that's all the possible outcomes, and calculate the probability. Each branch in tree diagram represents a possible outcome. If two events are independent, the outcome of one has no effect on the other, as we discussed. So for example, if you toss two coins, getting heads with the first coin will not affect the probability of getting heads with the second. A tree diagram is useful for portraying conditional and joint probabilities. It is particularly useful for analyzing business decisions involving several stages. The tree diagram, seen here on the right side, okay, is a graph that's helpful in organizing calculations that involve several stages. Each segment in the tree is one stage of the problem. The branches of a tree diagram are weighted by probabilities. So if you look at this example is flipping coins, so there's a 50% chance of getting heads and there's a 50% chance of getting tails. And then you have the second coin, and you're flipping it, heads and tails, that's 1/2 and 1/2. If you had tails here, getting heads and tails is 1/2 and 1/2, and the third coin is 1/2 and 1/2. If heads, tails, heads, tails, heads, tails, heads, tails, it's all 1/2. Okay? Does everybody understand this concept of a tree diagram? How you would actually draw it? You are looking at all the probabilities that are possible given whatever the problem is. Okay? So if you think about it logically, you're just going in steps. What are all the possibilities? And you figure out what are the probabilities of each of these happening. I mean, this is rather simple. This is flipping a coin. Okay, so the tree diagrams allow you to see all the possible outcomes of an event and calculate the probability. Each branch, okay, these are branches, and even these are branches. If two events are independent, the outcome of one has no effect on the outcome of the other. So for example, if you toss two coins, getting heads with the first coin will not affect the probability of getting heads with the second. And from this tree diagram, you can see that there are 8 possible outcomes. That's with flipping it 3 times with 3 coins. To find out the probability of a particular outcome, you need to look at all the available paths, the sets of the branches. The sum of the probabilities for any set of branches is always 1. It's a probability, so you know it must add up to 1. And you should also note that in the tree diagram, to find a probability of an outcome, you can multiply along the branches and add vertically. So multiply along the branches and add vertically. Okay, so the probability of 3 heads is, probability of 3 heads is 1/2 times 1/2 times 1/2 equals 1/8, as seen in the video that we did see. The probability of 2 heads and a tail equals the probability of head, head, tail, plus the probability of head, tail, head, plus the probability of tail, head, head, equals 1/2 times 1/2 times 1/2 plus 1/2 times 1/2 times 1/2 plus 1/2 times 1/2 times 1/2 equals 1/8 plus 1/8 plus 1/8 equals 3/8, and it should be, let's see, 0.375, I believe, so 37.5%. Yeah, that's what was in the video. Any questions about the tree diagrams? That's all we're going to do about tree diagrams. You do it more if you're going to take STAT 2011. So, any questions about that? No questions? Okay. So we finally finished chapter 4. All right. So as I mentioned in the announcement, the chapter 4 test will be available from 5 o'clock on Friday to 5 o'clock on Monday. Okay. So my suggestion is look at the PowerPoints, look at the videos, look at the textbook, look at the examples from my lab. Okay, it's going to be the same as the previous test, so you'll have 2 hours to complete. All right. How to print slides? Have you never printed any PowerPoint slides before? John? It's just like printing a file from Word or a file from... I don't remember how many questions going to be. You know, I can tell you before, in the class on Friday. Okay? All right. So, and as you would say, thank God that's finished. Well, it's 2 hours. You'll have 2 hours to complete it. I don't remember exactly. Okay, so I'm going to see if we can get this to work. No, you should be able to finish the test. Okay, not a problem. Remember what I described here. I don't know, John. I don't remember how many questions there are. I will tell people on Friday how many questions there are. Okay? So I'm going to try to see if I can get this video to work. Probably will not work. Why? I don't know. Okay. Oh, well, here's what works. No, it didn't work. Okay. I have no idea why this is not working. I must figure this out. Okay, sorry about that. Okay, so a video, you can watch it from your place. Okay. So this chapter is about discrete probability distributions. So we learned about frequency distributions, and this chapter is about probability distributions. All right. So these are the learning objectives for this particular chapter. Define the terms probability distribution and random variable. Distinguish between discrete and continuous probability distributions. Calculate the mean, you know what that is, the variance, what that is, the standard deviation of a discrete probability distribution. So you know what mean, variance, and standard deviation are. We haven't talked about a discrete probability distribution, but it's similar to the same calculations. You'll learn how to describe the characteristics of and compute probabilities using binomial probability distribution. Does anybody know what binomial may mean? What does bi mean? What is a bicycle? How many wheels does a bicycle have? 2. Correct. That's when you look at this, the bi, I think it's Latin, I'm not sure, means 2. So it's 2 and nomial, 2 number probabilities. Okay, so you know it's 2 probability distribution. You will also describe the characteristics of and compute probabilities using the hypergeometric probability distribution. And we talked about hypergeometric, I believe, in chapter 2. And the final thing is describing the characteristics of and compute probabilities using the Poisson probability distribution. Has anybody heard of the Poisson probability distribution? Nobody? You didn't? Anybody taken economics? John, you've heard of it? Yes, no? Oh, from last semester. Okay. All right. So apologize for the video. So please look at the videos, after, especially for chapter 4. So a probability distribution is a discrete probability function is a function that can take a discrete number of values, not necessarily finite, so it doesn't necessarily go to infinity. And it's most often non-negative integers, remember. So it does not include 2.6, 10.5. They're integers, or some subset of the non-negative integers. There's no mathematical restriction that discrete probability functions only can be defined as integers. But in practice, this is usually what makes sense. So for example, if you toss a coin 6 times, you can get 2 heads or 3 heads, but not 2.5 heads, right? That's the definition of discrete. When we're talking about statistics. There's no such thing. When it's discrete, it's just an integer. Okay? And each of the discrete values has a certain probability of occurrence. That is between 0 and 1. As you know, it's still a probability. It's still a percentage. So that is a discrete function that allows negative values or values greater than 1 is not probability function. So first important point, it is not a probability function if it allows negative values or values greater than 1. The condition that the probability sum to 1 means that at least one of the values has to occur. It can be 100% and the other one 0%. So, what are the characteristics of a probability distribution? The probability of a particular outcome is between 0 and 1 inclusive, just like the other probabilities that we just talked about from chapter 4. The outcomes are mutually exclusive events. The list is exhaustive, so the sum of the probabilities of various events equals 1. So here we have an experiment. We toss a coin 3 times. Observe the number of heads. Possible results are 0 heads, 1 head, 2 heads, and 3 heads. So what is the probability distribution for the number of heads? So here's your possible results. Coin 8 times. There's circumstances are 8, and here's the coin toss, first, second, third. So the first is true, 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 and the number of heads is 0. Okay, 0 heads. There's 3 tails. Okay, It's really important for you to understand how to read tables. And we're going to read more and more tables, and it's really important because it actually makes things easier when you understand what the tables are. Okay? So in the second one, you have tails, tails, head. So the number of heads is 1. Okay, we go down, get down to the possible result, the 8th one, where it's 3 heads. So the number of heads is 3. Okay, so here's your possibilities. 0 heads, 1 head, 2, and 3. With 0 heads, the probability of having that happen is once, okay? Because you only see the 0 here one time. So it's 1 over 8, which is 0.125 or 12.5%. The number of heads was 1. That happens 3 out of the 8 total. So we have this one, and this one. And that equals 0.375 or 37.5%. The number of heads is 2. We have 1, 2, 3. Again, 3/8, 37.5%. And if you have 3 heads, it's 1 over 8, which is the same as 0 heads, 12.5%. You total this up, you have 8 out of 8. You total up the probability, and it should always equal 1. When you make a graphic representation of this result, okay, on the vertical axis, you have probability. 0 to 3/8, that's the highest. Or you can, my preference is if you put in the percentages here, as opposed to the fractions. You have 0, it's 1/8. You have 1 head, okay, 3/8, 2 heads, 3/8, 3 heads, you have 1/8. Are there any questions about that? So everybody understands it's the same as the other probability, okay? And it's the same in graphing. So are there no questions about that? All right. Okay. A random variable. So I assume everybody did your algebra in your initial math. So you know you assign the variable x to your unknown. In this case, we're talking about a random variable. All right. I'm just going to check something. And I want to see if we can get the video. Doesn't appear to be. Oh my God. Okay. Sorry, everybody. I know it's not very conducive for learning here. I'm just going to try one more time, and if it doesn't work, it doesn't work. No, it didn't work. Okay. Sorry. Anyways, back to here. Okay. So a discrete random variable is one which may take on only a countable number of distinct values. It can be 0. Okay, they're integers and can go to whatever. And discrete random variables are usually, but not necessarily all the time, counts. Okay, and what is a count? What's another word for a count? Anybody? What's a count? The count from Sesame Street. Nobody knows what a count is. If you count cars in a parking lot, what does that count? Oh, come on, people. You know what this is. Nobody knows what this is. Oh, a number. Okay, Amir. What kind of number? What do we talk about? A random number? No, a count is not a random number because you're doing it on purpose. Isn't it a frequency? You counted the number of cars in a parking lot. Yes, exactly. Okay? Okay, people, I want you to read the book. I want you to look at the videos. Okay, you're not going to get hints during the test. Okay? And this is basic information. You're doing a count. So what are you doing? You're counting something. It's a frequency. Period. Okay? It's simple. So if a random variable can take only a finite number of distinct values, then it must be discrete. So an example of discrete random variables include the number of children in a family. It can't be infinity in a regular family with children, with human children. Okay, we're not talking about bacteria. Friday night attendance at a cinema, right? Because you only have that number of seats. You can only fit in that number of people. Okay. So I want people, if you have a question, please ask the question, because this is very important to understanding about discrete numbers. The number of patients in a doctor's surgery or waiting room, the number of defective light bulbs in a box of 10. Probability distribution of a discrete random variable is a list of probabilities associated with each of its possible values. It's also sometimes called the probability function or the probability mass function. I do not know the origin of that term. Okay, so a discrete random variable is a random variable that can assume only certain clearly separated values. It is usually the result of counting something. So for example, for today's class, at 4:38, there are 16 people in attendance. Okay, that's a discrete number. It only happened today, Tuesday, October 13th at 4:38. Does anybody have a problem understanding that? Okay. So, second example, the number of children in a family. So look at your own family. How many children are in each of the family? It's a discrete number. Okay? It's not infinity. It can't be infinity. Okay, it can't be a negative number. It can be zero. Well, that can't happen in this case because you're all here. You're all part of a family. The third example, the number of cars entering a car wash in an hour. Okay? You set the condition. I want to count all the cars that enter the car wash. I'm only going to do it for 1 hour. It's going to be a discrete number. Okay, the number of home mortgages approved by Coastal Federal Bank last week. Okay? It's a condition that you can measure, and there's going to be a number. It could be 0, it could be 100. It doesn't really matter, but it's a discrete number. A continuous random variable can assume an infinite number of values within a given range, and it usually is the result of some type of measurement. Okay, so an example, the length of each song on the latest Tim McGraw album. For those of you that like country music, he's a country music singer. We could take the weight of each student in this class. That's a discrete number, okay? It's a continuous random because it's on a continuous scale. the temperature outside as you are reading this book. Okay? The amount of money earned by each of the more than 750 baseball players currently on Major League Baseball team rosters. So in theory, it can go to infinity. Okay? So do people understand the difference between discrete random variable and continuous random variable? So discrete is counting, which is basically a frequency. Okay, you do understand, John, or you don't understand? And the continuous random variable is one that is a result of measuring. Okay? You're measuring. So we talked a little bit about this when we talked about frequency distributions. Yeah, discrete is counting. Continuous is measuring. You understand the difference between the two? Okay. Does everybody else understand? Does anybody else have a question about that? Okay, no questions. I will. Okay, we'll go to the next slide. So the mean, the variance, and the standard deviation of a discrete probability distribution. So the mean, we know, is the typical value used to represent the central location of a probability distribution, right? The mean of a probability distribution is also referred to as its expected value because it's the mean. That is the expected value. All right, and we're here, the case is we're using mu equals the sum of x times the probability of x. Okay. The variance and standard deviation that measures the amount of spread, dispersion. The computational steps are you subtract the mean from each value and square this difference. That gives you the variance. Multiply each squared difference by its probability. You sum the resulting products to arrive at the variance. And the standard deviation is found by taking the positive square root of the variance. This is exactly the same as done before, except for this is for a discrete probability distribution. Okay? And everybody remember, so here sigma squared equals the sum of x minus mu. You square that. There's a probability of x, gives you the variance. You take the positive square root of it, and you get the standard deviation. Okay, so here's an example. John Ragsdale sells new cars for Pelican Ford. John usually sells the largest number of cars on Saturday. He has developed the following probability distribution for the number of cars he expects to sell on a particular Saturday. So, when he's not sold any cars, the probability is 10%. He sells one car, it's 20%. Two cars, 30%. Three cars, 30%. Four cars, 10%. The total, 100%. Or when we're looking at the decimals, 1. Any questions about that? Everybody get that? Okay. So the mean, we take the number multiplied by the probability. Here's the probabilities. Okay, add them up, and we get 2.1. Okay, that's the mean of the discrete probability distribution. So the number of cars sold, 0 to 4, we have the probability. Okay, we have the mean times the probability, we get these numbers. Remember, this is a number, 0, so multiply that by 0.1, you get 0. Okay, so the mean comes up to 2.1. Okay, not doing anything different. So the variance is, here's the probabilities. Here's the mean, sorry, here's the number minus the mean. Okay, we square it, we get this number. Okay. We end up with this. Add them up. We end up with sigma squared equals 1.290. That's the variance. Okay, that's the spread of the data. And the standard deviation is basically taking the square root of the variance. In this case, it's 1.290. Square root is 1.136. So I will just mention, when you are doing this or you are calculating the mean or the variance, in this case, you can shorten it to 1.29. That's not a problem. But when you're figuring out the standard deviation, please round it to 3 decimals. Okay? I know that we talk about rounding to 2 decimals, but in this case, when you're doing the mean, the standard deviation, the variance, I would like it at 3 decimals. So is there any questions about this? No questions. Okay. So we'll stop there and we will continue on Friday. And if anybody has any questions other than today or about today's class, remember I have office hours tomorrow from 10 to noon. And everybody have a good evening. And we'll see everybody on Friday. Okay? Thank you.